Ja, herzlich willkommen zum heutigen Anlass der Werkstückhalle. Ich freue mich, sind wir wieder hier im blauen Saal vor Ort. Zusätzlich streamen wir den Anlass und haben weitere Zuschauer extern. Ja, die fortschreitende Klimaerwärmung macht CO₂-armes und ressourcenschonendes Bauen dringend notwendig. Aufgrund seiner vielen Vorzüge ist Beton weltweit der meistverwendete Baustoff. Gleichzeitig verursacht die Zementherstellung einen beträchtlichen Teil des globalen CO₂-Ausstosses. Darum kommt dem Umgang mit Beton im Kontext des Klimawandels eine entscheidende Rolle zu. Die Werkstückhalle widmet sich in diesem Jahr dem klimafreundlichen Einsatz dieses allgegenwärtigen Materials. In unterschiedlichen Formaten werden mit diversen Fachleuten CO₂-arme Betone, Urban Mining und materialeffiziente Konstruktionen vorgestellt und diskutiert. Der erste Anlass hat bereits stattgefunden. An der Werkbesichtigung Anfang Juli zeigten Patrick Eberhard und Team, wie bei Eberhard Unternehmungen, Bauschutt fachgerecht aufbereitet und als hochwertiger Recyclingbeton, genannt Zirkulit, wiederverwendet wird. Zirkulit ist ein zertifizierter RC-Beton, bei dem 3/4 der Bestandteile aus Sekundärrohstoffen bestehen. Ein sehr hoher Anteil, gewöhnlich liegt der Anteil der rezyklierten Gesteinskörnung eher bei 25–40%. Durch eine neuartige Speichertechnologie wird er zusätzlich mit CO₂ angereichert, womit bestehendes Kohlendioxid aus der Atmosphäre gebunden werden kann. Ja, Zirkulit ist neben weiteren Rohstoffen und Materialmustern in der Auslage der Sonderausstellung zu sehen. Sie möchte Materialwissen zum Thema vermitteln, aber auch anhand geplanter und gebauter Beispiele aufzeigen, wie vielseitig und allgegenwärtig das Material ist. Beton ist durch seine Anpassungsfähigkeit auf vielfältige Weise formbar und eignet sich damit für die unterschiedlichsten Bauteilgeometrien. Er besteht aus nicht brennbaren Komponenten und ist witterungsbeständig. Er ist im Schallschutz ein beliebtes Material und kann auch thermisch aktiviert werden. Je nach Ausbildung der Bauteile hat er eine hohe Druck- und Zugfestigkeit sowie Feuerwiderstandsdauer, ist wasserdicht, frostbeständig und sehr langlebig. Die vielfältige Gestaltbarkeit des Baustoffs und seine zugleich stützenden, trennenden und schützenden Eigenschaften bieten ein enormes Potenzial in der Anwendung. Das ist der Grund, dass er nahezu bei jedem Gebäude und bei allen möglichen Infrastrukturbauten eingesetzt wird. Leider gibt es dabei auch einen Haken. Sein Bindemittel Zement ist für knapp 8% des globalen CO₂-Ausstoßes verantwortlich. Auf dem Kuchendiagramm sehen wir die Inhaltsstoffe und CO₂-Emissionen von einem Kubikmeter Beton. Zement beträgt von den Bestandteilen gesehen nur etwa 12%, löst aber 90% der Emissionen aus. Ja, wo können wir ansetzen und unseren Beitrag als planende, ausführende oder als Bauherrschaft zur Senkung der CO₂-Emissionen leisten? Neben den aktuellen Möglichkeiten im Bereich der Materialtechnologie bietet die Ausstellung auch einen Überblick über konstruktive Ansätze wie materialeffiziente und hybride Konstruktionen oder, was die CO₂-Emissionen um 100% zu senken vermag, der Erhalt von sehr dauerhaftem und wertvollem Bestand. Betontragstrukturen wie diese hier vom Toni-Areal in Zürich West können Generationen überdauern, wenn wir sie bei Umnutzungen und Umbau berücksichtigen. Ja, mit dem Interview Beton ist unersetzlich in der Hochparterre-Sonderausgabe 10/19 hat Professor Scrivener viele von uns aufgerüttelt und auch die Problematik der CO₂-Emissionen uns vor Augen geführt. Dies war der Moment, als mir klar wurde, dass ich selbst viel zu wenig weiß von den aktuellen Möglichkeiten, wie wir Zement und Beton in Zukunft einsetzen können. So ist die Idee zu dieser Ausstellung entstanden. Deshalb freue ich mich sehr, konnten wir sie für diesen Anlass gewinnen. Scrivener hat an der Cambridge University Materialwissenschaften studiert und arbeitete auch in der Forschung bei Lafarge in Frankreich. Sie war 15 Jahre lang Chefredakteurin der Zeitschrift Cement and Concrete Research. Seit 2001 ist sie ordentliche Professorin und Leiterin des Labors für Baumaterialien an der EPFL. Karin Scrivener ist Materialchemikerin und für ihre Pionierarbeit auf dem Gebiet der zementhaltigen Materialien weltweit bekannt. Sie setzt sich aktiv für die Förderung nachhaltiger Zemente ein und hat gemeinsam mit Partnerinstitutionen einen klimafreundlichen Zement entwickelt. Dear Karen, with the interview Concrete is Irreplaceable, in the Hochparterre Special Edition, you have shaken many of us awake and also made us aware of the problem of CO2 emissions. It was the moment when I realized that I myself still know far too little about the current possibilities of how to use cement and concrete in a climate-friendly way. That's why the idea for this exhibition was born. That's why I'm very happy to have you here tonight for the opening. Welcome, and please, Karen.
So Stephanie, thank you very much for the introduction, and thank you all for coming this evening. It's very nice to see people really and not the other side of a computer screen. I apologize I cannot address you in German. I could in French, but I don't think that would really be much help to you. Probably English is better. So what I'm going to talk about tonight is, concrete, what we can do about it. And I think, many people have this very negative idea of just what a lot of CO2 cement and concrete produce, but I thought we'd start with a little quiz. So I'm going to put up here several different activities and see if you can work out which of these has the highest CO2 emissions. So of course we have cement and concrete, iron and steel, clothing, passenger transport on the roads, food loss, food waste. So I'll give you a few seconds to think. Make up in your own mind what you think of these, which of these you think comes out on top. And then we'll have a look at the answers, and I think it might be a bit surprising. So cement and concrete is usually considered to contribute between 6 and 8% of world emissions. Iron and steel, almost identical, 7%. This one's the real surprise. Clothing, 10%. This is probably something we could all do something about. How many clothes do we have in our wardrobes we've never or hardly worn? Passenger transport, just passenger transport, not freight on the roads, 9.5, and food loss, 6. So the important point is, not to say that cement and concrete is nothing, but to say there's an awful lot of things that have this very significant contribution to CO2, and we need to think what we can do about all of these. Now, concrete has this emissions, but then if we look at the amount used, we see it's absolutely colossal. And it's really this that explains why it has such big CO2 emissions. You can see also the other materials here are really quite tiny in proportion. So, of course, in Switzerland, we discuss a lot about wood. Of course, wood is a wonderful material. I've got nothing against wood, but there's no way it can make a significant impact on concrete. In fact, if we wanted to replace just 1/4 of the amount of concrete we use with wood, we would have to plant new, sustainable forest 1.5 times the size of India. And, I think we know that there's so much competition for land use in the world, this is just simply impossible. So if we look at then the embodied energy in CO2, we also see again that concrete's way down in that bottom left corner. It has some of the lowest emissions per unit weight of any material we have. So all of these are not excuses, because we can still do a lot, and that's what I'm going to try and present to you. And if you want to read more, please have a look at this report we wrote a few years ago for UN Environment. I have 1 or 2 copies here. I can leave if anybody wants a paper copy rather than downloading online. And there's also several presentations on YouTube. For example, this one I did for Rylam a few months ago. So let's look where the CO2 emissions come from in cement. And here it's quite different from many other materials where, of course, energy is the major contributor. And we know nowadays we can eventually replace most forms of energy with renewable energy. But unfortunately, that's not really going to help in the cement business. We have this cement kiln here, which looks rather kind of primitive, but in fact, there's already been a lot of work to improve the efficiency of this process. It's already quite close to what is reckoned to be thermodynamically possible. And in fact, cement kilns can now be used very efficiently to get rid of a lot of waste materials, such as used car tires, old oil, plastic offcuts. All these things can be burnt in a cement kiln. We can therefore get their calorific value, and also because of the very high temperatures in the cement kiln, the chemicals are very efficiently broken down. Where the majority, about 60% of the emissions are coming from, is this simple equation on the right here, which is calcium carbonate, which is limestone, which is 80% of the raw material, during this process to make cement, breaks down into calcium oxide and CO2. And that's where most of the emissions come from. Some other things that are important to realize are where cement is being used today and in the future. Today, more than 90% is being used in developing or emerging economies like China, etc. I don't know what I did to that slide then. This China, of course, probably has peaked. It's reckoned that this is now decreasing, but there's many countries coming along behind. India, for example. In India today, the consumption per capita is about 1/5 of what it is in China. And of course, India wants to develop. There are still many people without decent housing, without even decent toilets. And this is going to mean that this proportion, about 90% in these countries, is going to stay like that. And that also means when we take this figure of the amount of emissions coming from cement, it's very uneven through the world. You see it's about 15% in China, but in the United States, only 3% of the emissions are coming from cement because they produce so much energy from other sources. And in a country like Vietnam, which produces an awful lot of cement for export, it's maybe as high as 25%. So what can we do? Well, I think the most important thing we have to understand is there's no one single solution. And what we really need to do, we need to work at all stages of the process. So I talked about producing cement, or more correctly, what's called clinker, which is produced in this cement kiln. And there already, there's been a lot of improvements. We can then work at the sorry, it keeps moving on me. We can then work at the cement level, replacing material in cement, and that's mainly what I'm going to talk about today. But that's not the end of the story. It's important we can follow through those gains into the production of concrete, into the buildings, where there's also significant reductions to be made, and also by more efficiently using and reusing buildings. And of course, it's very nice to be here in what's really a reused building. So, oh dear, I'm sorry, I'm having lots of problem with your computer because it does all sorts of funny things on me. Oh, right. So, first question people say, well, you know, most of the CO2 emissions are coming from limestone. Can we make cement without limestone? Can we make it with a different chemistry? Well, the short answer is no, and I'll try to explain to you why. Well, the main reason is we have to look at the composition of the Earth. It's always remarkable, no matter the hundreds or even thousands of times I've presented this slide, that more than 98% of the Earth's crust is made up of just 8 elements. That's oxygen, silicon, aluminium, iron, calcium, sodium, potassium, magnesium. So clearly, for something that's used in these enormous quantities, there's no point looking at all the other elements in that remaining 2% because they're going to be much too expensive and not available in the quantities we need. And then we need to think about how does cement work? Well, it's really a very interesting process because we start with this material where we have these gray grains floating around in water, and that's what makes it nice and fluid. You can make it into all these different shapes. You can transport it onto site. And then what actually happens, those cement grains dissolve. So that's like when you put sugar in your coffee or you put salt in your cooking water, it dissolves. But that is not, unlike your salt or your sugar, that's not the end of the story. Because then you get this chemical reaction between the things that are in the solution, and they form these new solids, which I've drawn here in red, which are called hydrates. And because those new solids incorporate water in their structure, they occupy a higher volume. And because of that, they join the cement grains together and give you this strong, rigid solid. So what you need something that's going to dissolve, but it's then going to precipitate these hydrates. So if we go back to this composition of the Earth and we look at the different oxides, what we find is that the oxides of sodium and potassium, they're too soluble. So they dissolve fine, but they don't deposit the hydrates. On the other hand, the oxides of magnesium and iron, here we have the opposite problem. They don't dissolve enough, so they just stay in the same place. So this means we go from the whole composition of the Earth to a system of just 3 oxides, which is the oxides of calcium, silicon, and aluminium. And we've been studying this system of 3 oxides for well over 100 years now. We know everything about it. We know all the phases that form. And we basically have 2 areas in this diagram of combinations between silicon dioxide, calcium oxide, and aluminum oxide, where we have cements, these materials that dissolve and then form these new hydrates. And we have this composition over here, which is what we call Portland cement, but it's basically made up of calcium silicates. And we also have this composition over here, which is where we find calcium aluminates and calcium sulfur aluminates. And at first sight, this is very interesting because this black area here is further away from this corner here. That means it contains less calcium oxide and therefore less CO2. Unfortunately, life is not so simple because the problem is to form these compounds, we need to have minerals that contain much more alumina compared to silica. And this brings us to minerals like bauxite, which is much more locally distributed. It's expensive. Of course, it's used to produce aluminium. And in fact, even if we took all the current world production of bauxite and diverted it to produce these cements, we would only be able to fill about 10% of demand. And that would mean we had no aluminium either. So clearly that's, they can be interesting in a kind of small scale, very small scale, but they're not really going to solve this CO2 problem. And then, there's other things that people talk about because nearly every week I have some journalists phoning me up asking about some publicity given to some supposedly wondrous solution. And everybody has this idea that there's going to be some miracle breakthrough out there that we haven't discovered yet. What I've tried to explain to you is that, we have this composition of the Earth. This is not going to change. We know about the chemistry of those materials. There's nothing out there to be discovered because you know, it's a solid material. It has to come from the earth, and people can't live in nano or virtual houses. And so a lot of these ideas people are coming up with are really verging on magical thinking or alchemy. So one of the most common fallacies comes back to this basic way in which CO2 is produced in the first place. So I explained to you we started with limestone. And that's very important because almost all calcium in the earth is already in the form of calcium carbonate or limestone. And during the production of cement, it gives off CO2, it forms these various compounds that contain calcium oxide, then these react with water, and over time, that concrete can reabsorb CO2. But I think it's fairly obvious it can never reabsorb more CO2 here than it gave off here, because that's the basic law of conservation of mass. So there's a lot of people who say, well, look, you know, if you add calcium oxide or calcium hydroxide to your concrete, it can absorb more CO2. Well, that's true, but where are you going to get the calcium oxide or calcium hydroxide from? If you get it from limestone, it already gave off CO2 during the production, and you've gained absolutely nothing. Other people have these wonder ideas that you can take algae and they can make calcium carbonate. Again, it's true. That's how limestone formed in the first place. It formed by these microorganisms in the sea, taking calcium and CO2 from the atmosphere. But only if you feed them a sort of calcium, which was not carbonated, is this going to go anywhere. So I think, you know, you can see that this really is just a nonsense. And in fact, if you have sources of calcium which are not carbonated, you can just easily use them to produce new cements. Then lots of other people talk about alkali activated materials. Well, the long and short of this is that basically they use these substitute materials, which I'm going to tell you in a few seconds, are in short supply. And therefore, you know, these are already used in cement. So again, we can have no gains here. And in fact, overall, we might have a loss because we have to produce the alkalis to activate them. And that's without talking about all the technical issues associated with these materials. So we have to face the fact that this Portland composition is going to dominate. And what we can do, we can substitute quite large proportions of this Portland cement with additional materials. And this shows you the worldwide figures. And the materials that are most used as substitutes are, first of all, limestone, then slag, which comes from producing iron in blast furnaces, then fly ash. Fly ash comes from burning coal to produce electricity. And you see in the 90s, this technology really took off and the level of substitution increased right rapidly. But for the last 10 years or so, it's more or less stagnated. And it's more or less stagnated for the simple reason that we don't have very much of these slag and fly ash. Slag, as I said, comes from producing iron in blast furnaces. Now we're recycling more and more steel. Of course, that's a good thing. But if you have more steel from recycling, you have less produced from blast furnaces. Similarly, fly ash. Fly ash comes from burning coal. Coal is the #1 source of CO2. And many coal-fired power stations have shut down. And of course, we don't have either of these materials in Switzerland. So we do have a lot of limestone, which is the most used, but the problem is we can't go to very high levels of substitution without simply diluting the properties of the concrete. And the one thing we do have, which is a real game changer, are clays. Clays are super abundant, they're available everywhere, and they can be simply what's called calcined, that's to say heated, in the range only about 800 degrees, so much lower than making cement. And this is what led us to this technology we call LC3. LC3 stands simply for limestone calcined clay cement. We started off calling it low carbon cement, and then we realized everybody was calling their solution low carbon cement. So we just wanted to be factual. And what's interesting about this LC3 is that by putting the calcined clay together with limestone, we can go to much higher levels of substitution. So this would be the composition of, say, a cement including fly ash. You would have about 70% of the Portland cement and about 30% fly ash. Now, in LC3, we can take out another 15% of that very high CO2 emitting cement and replace it with limestone. And limestone, if it's just ground up, it's not heated, then it's a very low CO2 material. And with this, we can gain similar strength to the reference Portland cement. Slightly lower at 1 day for this experiment, but you can actually bring the strength back up even at 1 day by grinding and other technologies, and by 7 days it's stronger, 28 days it's stronger. So here we have 50% less of the Portland cement. This amounts to 40% less CO2 emissions, similar strength, and some properties like, for example, resistance to chloride ions and alkali silica reaction are very much improved. Now, the reason we can get this very good reaction is because of the clay structure. Clay has this layered structure. You can see this is at the atomistic level. You have a layer of silicon and alumina together, and when you heat these up, they become disrupted, and then, in fact, the alumina can react with the limestone to form these compounds here, which fill space and contribute to strength. So we've now tested more than 70 clays from all around the world, and basically we see the performance correlates simply with the amount of kaolin in this structure. Kaolin is one specific clay type, but it's distributed very, very widely around the world. So in these maps, anywhere you see this kind of yellowy-orange color, either in that one or that one, then you will have suitable clays. So you see this very, very widely available in those countries where the demand for cement is going up strongest, South America, Africa, Southeast Asia, but even in Europe, we've got very nice deposits. I didn't think there were suitable clays in Switzerland, but last week somebody told me that they've managed to find quite good deposits also in Switzerland, and some of the companies are trying these out to see if they work. And in many countries, these are actually waste materials. This picture's from India, and it shows the clay deposits which have been exploited for making, for making pottery, for making toilets, all these kind of things. And this is the waste material they can't use. And in fact, we've got better properties than the material people use today, the slag and the fly ash. So if we go back to this picture, which is the level of substitute materials in the world, you see this is stagnated just below about 25%. Now, on a basis of technical performance, we know we could go to a level of substitution on average of about 40%. So if we calculate this extra we could get, we can calculate this amounts to 400 million tons of CO2 per year. So that's, just to put in context, that's 10 times the entire emissions of Switzerland we could save on a worldwide level. And this is not just a nice idea in the lab. We've produced it in full trials. This is the demonstration house we built in India. We could calculate that this saved about 14 tons of CO2 compared to existing solutions. We can even use it in quite demanding pre-stressed applications. A quick look at some of the advantages and disadvantages. The first thing people said, people won't buy red cement. And clays are often red. Well, you could think, well, if it's low CO2, they should be proud of having red cement. But, apparently the market doesn't want red cement. You don't have to have red cement. You can have nice gray cement. There's a very simple technology coming from the brick industry. This shows the implementation of this technology commercially in the Ivory Coast. And you see you can have this nice gray color. People said, oh, calcined clays, they give you lots of problems of workability. It's very difficult to place them. Well, you can see here in this picture, you can produce very nice, easily flowing concrete also with calcined clays. And for these kind of placing applications, it can even have some advantages because the calcined clay avoids any problem of bleeding and segregation. You get very cohesive mixtures. In terms of chloride ingress, this black curve here shows you the chloride that has penetrated into the reference Portland cement after just 6 months. And the mixtures which contain slag, shown here in red, they're improved. The mixtures with fly ash, again, they're better still. But the best of all are these mixtures with the calcined clay and the calcined clay with limestone. And then people say, well, what does this cost? Again, good news, because it can be cheaper to produce than the existing materials. This shows the feasibility study. The red line is the reference for producing the Portland cement, and these are the bars for producing the LC3, depending on how far you have to transport the clay. So if you have the clay very close to the plants, then that's obviously the best situation. But even transporting from 200 kilometers, it can be feasible. And particularly interesting in grinding plants. Now, this is the situation in many parts of Africa because Africa doesn't have many deposits of limestone. And that means many countries, in fact, are importing cement clinker and then grinding it locally to produce cement. And if you do, they haven't got much limestone, but they have got lots of clay. And if they produce calcined clay locally, they can produce very big savings compared to the reference Portland cement. So finally, it's been a big effort. We've been working on this in terms of really technology transfer, getting the message out there for about 7 years now. And finally, it's taking off. Last year, we had the first 2 commercial productions starting in Ivory Coast and in Colombia. And this map shows you the different levels of interaction we have with different countries. So before I finish, I want to come back to the slide I showed you earlier about the value chain. And I want to emphasize the fact that please don't forget what happens next, because it's all very well having this 40% saving at the cement level. But if we use much more concrete, if we use much more cement in the concrete than we need to, that can more than wipe out all those gains. And this graph here shows you a compilation of basically the cement concrete of concretes according to their strength. And you see for exactly the same strength concrete here, you can have one that uses this amount of cement and one that uses this amount of cement, which is like 3 or 4 times more. So bad concrete technology can waste much more CO2 than using just pure Portland cement. And how do we get from these sort of not very efficient ones up here to these more efficient ones down here? Well, the first thing is to look for industrialized processes. Of course, in Switzerland, 90–95% of concrete is industrialized, comes from ready-mix plants, but that's not the situation in many other parts of the world. So we really need to push this industrialization of concrete because this is the first way of improving the efficiency. But we also have a problem of, coming from the way standards have been constructed. So these couple of slides show a very simple study we did in our lab. They were making concrete and they were using a cement content of 375. And I said, well, look, what happens if we make it with less cement content? We'll put in more superplasticizer to get the same fluidity, and we found that we could quite easily go down to a cement concrete of 225. That's like a saving of almost 30%. And then, of course, the workability gets crazy, and it was really no good. And in terms of strength, the strength's actually better when we have a lower cement content. You'll have less problems of overheating. You'll have less problems of shrinkage and cracking. And then if we look at all of this in terms of CO2 savings, you can see you can save as much by working at the concrete level as you can by working on your cement itself. So this is a very simple thing. People say, well, you have to use more admixture, but the price of the extra admixture was way more than compensated by the amount of cement you saved. Unfortunately, you know, most norms impose a limit for the minimum cement content. Typically 300 kilos per meter cubed is the limit for most specifications in Switzerland. So we could do a lot better than we are doing, but we can't go beyond that because unfortunately these norms were put together before the days of admixtures. And so that minimum cement content is what you would need to get the correct water-cement ratio without admixtures. So here there's also work to do. So this is just a simple illustration that, as I said, things don't stop at the cement level. You have to follow through to the whole value chain. So just to summarize that, I hope I've managed to convince you that Portland cements are here to stay, and what we need to do is work on this technology of introducing more supplementary materials. Because of the shortage of slag and fly ash, the only realistic option to do that on a scale, on a global level, is calcined clay. And we can really get very good properties with only 50% clinker and with clays that have quite a low kaolin content, which can be available as waste. And these can have advantages, particularly in terms of certain durability issues like chloride ingress, which is the #1 problem, and alkali silica reaction, which, for example, is affecting about 20% of our dams here in Switzerland. So I think this LC3 has a very serious role to play in lowering the CO2 emissions of cement and concrete. And I'd like to thank you for listening and hope that you found something of interest and maybe you have some questions.
Yeah, thank you very much. One of the first things which I kept in my mind, we have to change the norms. Is that true? That,
yeah.
What would you suggest to?
Well, I mean, people are already working on that. A little bit the issue is that people, you know, it's like the best is the enemy of the good, as sometimes people say. So people say, well, we should be able to have what's called performance standards. Instead of having this rule, you have to put this X amount of cement and this water-cement ratio, we should be able to have performance standards. The problem is it's really difficult to judge performance when you're talking about a building that's going to be there for 50, 100 years, and you want to do a test in the lab in a few days. And so for more than 10 years, people have been arguing about this and nothing's happened. Where you actually have a very simple thing, if you just got rid of these minimum cement contents and just focused on water-cement ratio, which is the important criteria, you could already make a step in the right direction very quickly. But, you know, as I say, people say, oh, well, yeah, we've got to go to the performance standards. And honestly, this will take another 10 years. And that's very sad because we haven't really got 10 years. You know, we know by 2030, we've already got to reduce CO2 emissions by 50%.
Well, it's quite a lot, yeah. On the other side, we are an architecture school besides a civil engineering school. What do you think about the impact of the design on concrete use?
Yeah, well, this is also, I mean, I didn't show the graph here because I knew I was going to be running over time, but, you know, like I showed you this dispersion with this concrete, you've got a similar dispersion with the amount of concrete you need to get a certain building. I mean, this shows you that you've got a dispersion between 1 and 4. You've also got an equal dispersion in a building. A most efficient building can be using 4 times less concrete than an inefficient building. And, you know, this is very important because, you know, we have this big debate what material we should use. And the wood lobby says, look, I can build this building in wood and it's got this amount, and this building in concrete has got that amount, which is much higher. But that's not true. If you build efficiently in either wood or concrete, you come to about the same embodied CO2. But if you make a comparison with an inefficient building, of course you can make any argument you like, and you can make it both ways.
Well, in Switzerland, we are especially inefficient. If I think at the 28 centimeter ceilings we build today as a standard. But it's not the civil engineer who tells us that we have to build 28 centimeters, but it's the acoustic engineer.
Yeah, okay, there's an awful lot of things like that. I can't pretend to be an expert on that. There are other people who are more studying that than me. But certainly it's well known that floor slabs, often you can save 50% of material without much loss of acoustic properties. I mean, and there are other ways you can diminish acoustic properties. And that's perhaps also an argument for, if you're going to use this massive amount, well, perhaps you don't need to make it to the same strength. I mean, I was speaking to some people in the UK who'd done a study on precast units, and the design strength was 40 megapascals, but the concrete was made to 70 megapascals because they wanted to have the strength at 24 hours. Okay. And then if actually they'd gone back to the designers and say, well, we're building it with 70 megapascals anyway, can you take some out of the design? The answer was yes. It's just very simple things like this. Well, they sound simple, but they're actually very difficult because the whole way the process happens has become so kind of, divided, and people aren't talking together.
And what do you think if you look at the infrastructure construction in this country, tunnels, bridges, and so on? Sometimes it seems to me that's quite a lot of concrete we use there compared to a...
Yeah, but that's what you see. But in fact, usually the amount of infrastructure is the minor part, and the housing and everything is the major part. And of course, the infrastructure, we do have a very huge criteria that we want this to last very long times. We don't want to replace tunnels every 10 years, whereas buildings often are demolished after maybe 40 years, not because they've worn out or not performing, but just because we want to build something else in their place. So, this is the sort of thing we need to think about.
Well, that's true. That's where we should keep the buildings a little bit more. So I want to open the discussion to any question? Yeah.
Also, I have two questions. Clay, I understand. What is calcined?
Calcined.
Yeah, calcined
so calcined just means heated up. So you have to heat the clay to about 800 degrees to activate it. Yeah. If you just use raw clay, it's not going to work. But you heat to about 800 degrees, and then it becomes this active material because the whole crystal structure gets completely disrupted. And then it reacts with calcium hydroxide, it reacts with limestone, and it gives you these good properties. Yeah.
And in your calculation, you had calculated how much fuel you need for heat to 800 degrees. That's quite a lot.
Yeah. It's much less. And the important thing, you don't have any of this chemical CO2 given off by the breakdown of limestone. So roughly speaking, for forming a ton of clinker, the typical CO2 emissions are about 850, and for calcining the clay, it's about 1/4 of that.
Okay.
Yeah. But this is all taken account of in our calculations, yes.
And the other question is, I'm not sure, have you presented a diagram about resistance against Carbonatisierung? I don't know this expression in English.
Yeah. I mean, the carbonation doesn't really doesn't change the resistance. No. Oh, yeah. Sorry, you mean resistance to carbonation? Yes. The carbonation will be somewhat faster because that's the same with all substituted materials, but it still meets the norms for typical constructions.
Because that's an important question. Our infrastructure buildings, they are planned for 100 years or more, and we have, if we have problems with the carbonation.
No, it meets the norms for these applications.
Okay.
But, more generally, that's also an area where we need to work on because, we have this carbonation. and this can lead to reinforcement corrosion. But generally, the reinforcement will only corrode when it is in a very wet condition. So interior concrete like this, you know, this wall is almost certainly carbonated. I don't know how old this building is, but it's almost certainly carbonated. But it won't corrode because it's too dry here. You have to have really moist conditions. So there's only a very small amount of buildings that are really susceptible to this. And this is a general issue, like, you know, changing the norms, that needs to be reconsidered in order to have more efficient construction.
Okay. Thank you.
Other questions?
I have a question. Where can I order LC3 cement when I'm convinced to build with it now?
You have to wait a little bit longer. We know that several of the major companies made quite a lot of trials in Europe this year. So Heidelberg, Lafarge Holcim will announce shortly that they will set up a small plant in France. So I think in about 1 year or so, you will be able to get it in Europe, and maybe quite soon in Switzerland. I mean, a lot of my information is confidential, so I can't say anything too explicit. But I do know that there are companies in Switzerland as well who are looking into this. So certainly from France, Germany, even Switzerland, soon, one or 2 years.
1 or 2 years.
Yeah.
And these Swiss firms will also contribute to the change in Asia?
Yes, yeah, I think that's what, you know, I mean, everybody asks me that, and, you know, of course it's important what we do in Switzerland, but it's much more important what's done on a worldwide basis, because, you know, Switzerland's going to stay quite a small country, and if we can save 10, you know, even if we went to zero in Switzerland, but with this technology, we can save 10 times that amount, you know, from a Swiss technology, which we can take out to the world. So I think it's important. We don't, you know, in terms of CO2, we should not just be looking, we have to do our stuff ourselves, but we should also be looking what we can do on a more worldwide basis.
Other questions? Well, thank you very much. So we'll start now the opening of our little exhibition. Stephanie prepared.
Ja, ich möchte alle jetzt einladen, nach vorne in die Ausstellung zu gehen. Dort ist ein Apero aufgebaut. Ja. Vielen Dank fürs Interesse und thank you very much for your input, Karen.
You're welcome.